Hi everyone, welcome back to the channel. Today's video tackles a fundamental yet crucial topic, analyzing RFT data to determine fluid density and type using Microsoft Excel. We will focus on an ideal scenario with three distinct and underground fluids and RFT measurements free of anomalies and supercharging effects. First, let's access the RFT data. Open Excel and navigate to the File menu. Click Open and locate your RFT file on your computer. Select all files for file type and then select the RFT file and click OK. A warning message might pop up. Just click Yes to proceed. In the text import wizard, ensure delimited is selected. Click Next. Select tabs and click Next. In step 3, select the column containing the date and choose day, month, year. Click Finish to import the data. Now we have RFT data imported, and this contains X, Y, Z coordinate, measured depths, well name, pressure, and type. We can import RFT data in copy and paste techniques. To RFT data on PUC. Open this file using any text editor, like for example the Notepad. Copy RFT data and paste it in Excel. While copy and paste might seem convenient at first, it can lead to error. So it's recommended to avoid it. Let's delete for avoiding duplication, and we work on this data now. Let's start with visualizing this pressure data using Excel plot. Pressure should be on X axis, and measured depths or the true vertical depths. It's the same in our case. On y-axis, per company, and just reverse the order. So we have depth increase downward. Do some format for this graph or plot. On the x-axis we have pressure measured by PSI, and the vertical axis is depths, measured depths, measured by meter. The plot we see here is quite interesting. It reveals three distinct clusters of data points, each with its own trend. To make things clearer and avoid any confusion, let's assign a unique color to each group. For now, these colors are chosen at random and don't hold any specific meaning.
So let's use yellow for example, and red for the second data series, and blue. This is just an example. We can change this later.
So, to understand these trends better, let's replot the data into three separate data series. The first one, the yellow one. The second one, the red one. And the third data set with blue color. So now we have the three data sets here. Let's change the color so we have consistency between the plot and data colors. Next, we will add a trend line to each data series. We'll get a curve fit gradient for each data set by using a trend line. We use a linear trend line, display equation, and R squared. We do the same for the second data series. I think now it's good enough. Display equations and R square. And what's the second one also? The trend line equation provides the slope of the line. We call it slope or curve fit gradient. which is for the first one 20. We can just read it directly from the equation, or we can use slope function. I prefer using slope Excel function. As first data set, we have the same number, you see. And the last one. So now we have the slope of these three straight lines, which represents as, the gradient measured by meter per psi, which for now this doesn't make any physical meaning. So what we need is actually a pressure gradient, which is a reciprocal of this slope of the line slope. I mean, straight line slope. We just we can get the pressure gradient from just calculating the reciprocal of the line slope. So now we have the pressure gradient psi per meter, and we also can calculate the pressure gradient measured by psi per feet, for example. Before we maybe before calculating the fluid density, we can do this. psi per feet, and we use the convert function, Excel function, to do this. Convert from meter to feet. Using convert function, we can also convert pressure gradient to density. Let's start with calculating fluid density in libra per cubic feet. To do that, I'm also using a convert function here. Of course, you are free to use other techniques or tools, so it's up to you. So we calculate the fluid density first in Libra cubic feet. So then gram cc, and again using convert functions. Once you have the fluid density values, you can leverage them to potentially identify the type of the fluid present. As we know, different fluids possess distinct density ranges. By comparing your calculated densities with established reference values for various fluids, we can obtain this from handbooks or online resources. And so we can differentiate between the three fluid groups we observed in the plot. Let's take for this example, let's take 42 kilogram cubic meter per as a limit between gas and oil. So if density less than 42 kilogram per cubic meter, we consider this as a gas. More than 42 and less than 1000 cubic meter kilogram per cubic meter will be oil, and more than 1000 is water. And you can see that we have three different fluids. The blue one represent gas, the orange one is oil, and the gray one is water. There's no single magic number to differentiate fluid. The densities often overlap. Density alone can be misleading. Temperature and pressure and other factors also influence fluid density. So it's highly recommended to consider other source of information and techniques, like for example using integrating BVT data. and maybe using petrol analysis also. Please be noted that these densities obtained from RFTs in reservoir conditions, so we need the formation volume factor to convert this to service condition. And also we can use RFT data get information about fluids contacts. And also we have to mention here that this we can use all this analysis using Petrol RE. Are you curious about how to determine fluid contacts from RFT data or how to perform this analysis using Petrol? Leave a comment below. Don't forget to like this video and subscribe for more content, and see you next time.